Hello there, welcome to the channel, welcome to the video. My name is Will, and if you've clicked on this video, it's great that you've come to join this walkthrough. So what are we going to be doing today? Basically, what I want to do is to respond to the request of a viewer of one of my other videos. Basically, I covered the topic of Viewport3D in about one or two or so videos, and I kind of focus more on the generation of the geometry, simplistic 3D primitive geometry such as cubes, cones, how to do that with Viewport3D C# and the XAML markup. Excuse me. However, a particular viewer actually asked how to animate geometry created via Viewport3D. So what I want to do today is to literally go over that, how to translate, rotate, generally animate 3D geometry via Viewport3D. So without much further ado, let's get straight into the video. What I'm going to do, please excuse me, my throat is a little groggy today. I'm just gonna fire up an application, and this is Morph CE. It's not finished, but it is an application I started writing a little while back, and it just generates 3D geometry, and you can manipulate such geometry in a variety of a couple ways. So without much further ado, you'll see two arbitrary cubes on the screen. If I go ahead and just scroll with the mouse wheel, you notice they start to move. One of them kind of flips around as they both zoom in, and the other just zooms. And if I scroll the other way, i.e. scroll backwards, the objects start to zoom away. If I hold the left button and start scrolling, I can translate that cube, the Earth kind of cube, away. And in the opposite direction, the cube starts to come in. There we go. So enough of that demonstration, just to kind of show you how it looks when it's animated, and you can kind of imagine the sort of things you can come up with some clever functionalities or algorithms, whatever you want to do. Your only limit would really be your creativity. So I'm not going to touch too much on the XAML side of things because we're going to be touching on rather animation. What we want to do is actually look at the C# logic and how to a certain approach to animating via the C#. So one of the first things you want to do, what I've gone ahead and done, I'm just going to have a quick sip about that, guys. What I've gone ahead and done, so we don't need to know too much about what's going on overall. The application does many different things, but for now, what I want to draw your attention to is I have a function here, and this particular function is the mouse wheel scroll event. It's called Viewport2_mouse wheel, and what happens is every time I scroll the mouse wheel within the viewport, then what actually happens is that this function is called. And now I have a bit of logic here that basically says, okay, if the mouse, if the e.delta, which is basically, e is just accessing members of the mouse wheel event arguments class, and what it does is says this member called delta, which represents the velocity of the mouse wheel, if it's going in one particular direction, which here is represented by the value 120, then I want to do something in particular. And then I've also said on the flip side, if the wheel is being scrolled in another direction, I want to do something else. So that's the first kind of concept. I'm sort of already tying in the user interface control with the actual geometry. So with that out of the way, what we actually want to focus on is the way that we apply the transformation, and it's actually rather simple, more simple than it may seem, and you're going to see what I mean by that, hopefully. So basically, all that we do is, or all that I did here at least, there's probably different ways you can do this. I've gone ahead and called a system.windows.media.media3d translate transform 3D class, and I've instantiated that class. So it's called translate transform 3D. Excuse me. And I've gone ahead and created a new instance of that class. And just so you know, the namespace for this, oh, I've already said, of course, System Windows Media 3D, part of the .NET framework, so you should be able to access it if you're using the .NET framework, or applicable versions of the .NET framework. As this particular application was written in the .NET framework, so obviously it's not the latest version of .NET, but Viewport3D is deprecated anyway, above a certain outside of the .NET framework, as far as I'm aware. So you won't find this namespace with, actually, you might find it with latter versions that are working with WPF. I'm not 100% sure, but in any case, if you have access to this, you want to use this class. Now, in that translate transform 3D instance, I went ahead and I accessed the offset X property, and I've gone ahead and set it to 2. And we're going to kind of see where that ties in. So now I have a class, and this kind of goes into the way that the geometry is generated, and I will go into detail how this is done a little bit, just so that it makes sense as to how I'm actually translating the geometry. So I made a class called Geometry Primitives 3D, and in that class we're accessing a collection called Vector Matrix. And then upon Vector Matrix, what we're doing, we're actually assigning it to the transformed version of the very same Vector Matrix collection. So this transform function, excuse me, which is obtained within the translate transform 3D class, is imposed upon the vector matrix, and we assign the vector matrix to the new vector matrix value. It's as simple as that, really. There's actually nothing that much to say, unless, well, there is a little bit more to say, because obviously there's a few more factors involved, and what I'll do is to explain how the geometry is generated. But this transform function is pretty useful and is what's used to actually transform the geometry. And by applying this offset X as 2, we're actually influencing the velocity, if I'm not mistaken. So the cube would move in one particular direction, 2 in this case, 2 being kind of like the magnitude, describing the magnitude, of course, innately the direction, -2 in the opposite case here, also describing the velocity, magnitude, and the direction, if I'm not mistaken. I haven't really explored this in a little while, so hopefully I'm accurate. So anyway, Geometry Primitives 3D, we're going to go ahead and have a look at this class. Do I have it up at the top? Yep. So the way I structured this is that cubes are, the whole idea of generating primitives is generally abstracted as this Geometry Primitives 3D class. And what this class does, it inherits from the cube primitives class. So, so what happens is the members of the cube primitive classes are accessible to Geometry Primitives 3D. So if you're familiar with inheritance, that should hopefully make a little bit of sense. So what are we doing here? Basically, we have a function, and this function is called Getcube. And Getcube is returning vector matrix. But as you can see, there isn't any kind of member in this class called vector matrix. But that's because we're actually accessing vector matrix from as an inherited member of cube primitives. So if I go ahead and have a look at cube primitives, we'll see that we have an abstract class. And in this abstract class, what we have here is the vector matrix right here as the field, but it's actually being accessed via its property, which is a public property I can't even speak today, exposing the private field. So this private field is a point 3D collection, and this is where a little bit of a recap might be needed. Oh gosh, I went ahead and clicked Microsoft Word when I actually have the I have the documentation on Google Chrome. So let me just go there. Okay, so reading it back a little bit, sort of touching on my older videos when I was speaking about kind of the theory behind things. So what we want to know is that vertices are, or vertexes are the corners where the lines of polygons meet. So if we have a simple square, you can see we have vector 0, 1, 2, and 3. Such is the case with a cube. We can observe the vertices as I've labeled on this cube. As you can see from this cube, I have labeled the vertices. They're labeled there. The vector is actually described as the positions value. So the positions holds a collection of 3D points. So we have 0, 0, 0, then we have 10, 0, 0, Then we have 0, 10, 0. So you can see the pattern there. And each of these describes a vertex. So you have this vertex, and this vertex. All of this, I suppose you could define that as a vertex points, but these are all just points in local space of the geometry. We don't actually know what connects to what, and that's where the indices vector comes in. So the indices vector, so this is not going to be too in-depth into this because I've already touched on it on the previous video. I might leave a link to the card or description below, or a link in the description below. We have triangle indices, which basically describes the index information of our geometry. And the triangle indices basically just defines how the vertexes are connected to each other, how the points of the vertex buffer, as it may be called, the vertex information is all connected. So again, I'm kind of just glossing over things just so we can have a little bit of an idea as to what we're doing in the code. All of this is better said in my previous videos, so have a look at that if you haven't already. So why did we need to gloss over that? So basically what we're doing here, we're creating a point 3D collection, so a collection of 3D points, 3-dimensional points. And what we're doing is that cube geometry basically just populates this collection with a specific set of points. So if you're familiar with defining 3D geometry from the ground up, you'll see that just even by eyeballing this sequence of vertex information, you can tell it's a cube actually. And I won't go into how that is really, but I will see if I can leave links to some resources that will help make sense of what I just said. But just know that these are just like essentially your X, Y, Z coordinate system. So on a discrete graph with X in the planes X, Y, and Z, you have 0, 0, 0, 10, 0, 0, 0, 10, 0, so on and so forth, or to define the point of a cube in local space. So once we have that defined, if we just reel things back and go back to the main window, we see that we're accessing that the vector matrix property, and within a loop. So we have a for loop here, and it actually loops between the values 0 and 8. And what is it doing? Index is being incremented at every loop, and we're basically applying the transform function on upon our vector matrix. And bearing in mind that we assigned the translate transform 3D class where the transform function is derived, there's a property there, if I can find it, I don't know where it's gone. Offset X has been set to 2, and so we're kind of defining a property of the transform itself. If I'm not mistaken, again, it's been a little while since I've explored this, but from what I can gather from the code, that should be just about right. So yes, so the vector matrix has the transform function applied to it, and then of course, what are we doing? I thought we might have been returning the values, but actually because the values have already been changed, then what comes next after the for loop, which by the way, this 8 represents the vertexes. So if I go here, go back to cube primitives, you'll see that we have 8 lines of vertex information. 1, 2, 3, 4, 5, 6, 7, and 8. That's why the for loop consists of 8 loops. Where's the main Windows CS file? So then finally, what we do after we've transformed the vector matrices in the back end, we go to cube geometry positions, and let's just have a look at what that is. Oh, okay, this is something for me to see as well. Okay, so that is just essentially a property in the mesh geometry 3D class. We don't have to worry about writing this. It's part of the .NET framework. So what are we doing? Let's go back. Cube geometry positions is equal to geometry primitives Viewport3D.getCube. So this is quite important. We're basically tying the positions value, which we find in the XAML, which represents the vertex information of the cube. We actually assign its value to the Getcube function. And the Getcube function, if we have a look at the Getcube function, it all ties in together because the Getcube just returns the vector matrix that we have transformed. And if that all makes sense, which I really hope it does, the result is a transformed object. So I'm just going to quickly go back. How am I doing for time? So that basically wraps it up. So I do hope that this makes sense. We simply are applying a transform function in order to deal with the translation of the cubes. Now I'm trying to see if there's a particular way I went through rotation. So the rotation, it's a little bit more simple. There's always ways to simplify. In order to create the rotation effect, it's quite simple. By the same token of rotating the mouse wheel, what we're doing essentially for the cube that rotates, at least, is we're looking at the rotate property. There's a property that has been named, or a field rather, it's named rotate, and it has access to this axis property. And as you can see, we're assigning it a new vector 3D. And I'm just going to home in on this rotate field so you can see where it is. It actually resides in the XAML, or at least it's defined in the XAML. And it is a part of the model visual 3D transform model visual 3D class dot transform. And then you have to nest within that a rotate transform 3D. So you need this particular kind of nesting if you want to deal with rotation. And this nesting, I won't go into too much details. This nesting is under the Model Visual 3D class nesting. Yeah, the Model Visual 3D namespace rather. So if you're kind of familiar with the way to scaffold the geometry in XAML, because it's quite tightly coupled with the CSharp part as well, then you shouldn't have too much trouble. I'll see if I can leave some links to some MSDN resources to help you in terms of the XAML side of things, so that you'll know how to set up the rotation in the XAML. And then comparably in the CSharp file, what we're doing, we're setting access to a new system, Windows Media 3D, Vector 3D. And then here's where things happen. So we are basically taking the value of this field, X rotate angle, which is defined as a field at the top of the C# file. It starts at 0. And we're just basically post-incrementing to modulo 360. So I won't go into too much detail into the modulo operator, but what it just basically means is that the value in focus here is wrapping around 360. So you can imagine I'm post-incrementing a value that started at 0 by 2. It will keep post-incrementing 4, 6, 8, 10, 12, so on. And then once it hits 360 and tries to post-increment beyond that, it will go back to 0. And then all we do, we assign this field's access property, the rotate field that I showed earlier. We assign the angle property, sorry, to the value of this x-axis rotate field. And that's as simple as that. So every time I turn the wheel, I get a rotation effect. And if you know anything about dispatcher timers, it's one way you can use to time your animations. In this particular example, I don't use a dispatcher timer. I don't know if I have one defined already. Maybe I intended to. I don't think I do. But look into the dispatcher timer, because then on the tick of the timer, you can also animate these features via some kind of bespoke update loop or something. But here I'm using the mouse controls to animate. And there you have it. That's a quick breakdown of how to animate and 3D geometry in Viewport 3D. I hope you found this video somewhat informative. Feel free to like the video if you found it helpful. Dislike the video if you didn't. Leave your comments and criticisms. All is welcome. And leave any kind of ideas you have for anything else you want me to do in regards to C#, Viewport 3D, or other related content on the channel. So without much further ado, I'm going to end the video there, and I thank you. So I just had to turn on my tablet here. I thank you very much for watching. Have a great day. Bye-bye.